Okay, should we go? It's a little bit too loud, I guess, but it should work. So good to go? Okay, hello. Welcome on this session about WebAssembly. As I see, you are 15 times more people than I have ever expected for this session. Yes, it's very, very experimental. Uh, yes, it's too experimental. We have some... Yeah, we can see it. Okay. So it's really experimental, and I'm quite happy to see so many people. Definitely, I thought only 3 people will show up. Although it's a Java conference, we'll talk about not so many Java things here. So a few words about me. I'm Dmitry. I work for T-Systems. I'm from the neighbor country, from Bulgaria. So it took me only 4.5 hours to get here with a car, which is quite good. I'm also just want to say that as a Java user group for the last year, we got the Duke Choice Award. We are very happy about it. So if you work hard, and like Romanian Java user group does as well, you will be awarded. This was unexpected for us, and we're quite happy about it. So let us say, I just like this slide. It's very pathetic. It's called Welcome to the Future. How many of you have heard about WebAssembly? How many have you just tried to do something with WebAssembly? Okay, so you can go. This is going to be a beginner session. I've never done a beginner session, so there will be some fundamental stuff. So I say welcome to the future, but when I first touched WebAssembly, this was my picture. Welcome to the past, actually. And I thought to myself, isn't this already, I've seen this somewhere, yeah, in the 90s. And during this session, we try to see if it's the same, actually, or not. So again, a small disclaimer. Well, first of all, we have to understand what is a WebAssembly, how can we use it, and then we will switch to Java usage of it. Because I'm a Java programmer, I'm not a web developer at all. So I like programming. And I use mostly Java for that. And for WebAssembly, we will also use Java. So we will also keep this small disclaimer about this KISS principle. We will keep it really simple and stupid. You know, many conferences, they start like, okay, we have a very, very easy example. Like, you know, this works like this. And then they show you this program. Yes. So, we'll not make it. And you'll be surprised. I hope you will be surprised with the idea that actually many simple tasks are still demanded in production, and they can be implemented like this. Okay, so what is a modern web? Like we know it right now. So most of the time on one side you've got a server which serves you something, like HTML, CSS, and JavaScript, but it produces it via a lot of different languages. So you are able to code in Java, Python, JavaScript itself, making it kind of a native, or even C++ on one side, on the server side. And on the client side, you are always bound to these 3 things. Yes, it's the HTML, it's the CSS, and it's and JavaScript. So where is programming on the client side actually? Many people say HTML is a programming. Well, I strongly disagree. HTML was not meant to be a programming. It's a markup language. It's not for programming, it's for markup. Yeah, some people say CSS is also programming. Sorry, I couldn't find funny picture why it's not. But it's not a programming. It's also, you know, styling. So the only programming actually on the client side is the JavaScript. And JavaScript was developed in 1995 by Brendan Eich, only in 15 days actually. And it's also not meant to be, well, exactly programming. It meant to be so much simple that non-programmers, the guys who actually do HTML, which is not programming, are still able to, you know, somehow put in control and orchestrate things. And JavaScript was kind of a good language for that. It's interpreted, it's dynamic weekly type, prototype based, well, everything you have heard in a previous presentation from Venkat. It's easy, it should be easy. This is its idea, it should be very, very understandable. Well, it was actually understandable at some point. In my case, that was just enough. You know, you have a web page, you make some fancy controls like, you know, alert message, for example, or something bumping out. That was just enough. But at some point, you know, something went terribly wrong. Yes, JavaScript was absolutely everywhere. Everybody say that Java should be the language that should run on every device, and this is wrong. JavaScript is the language that runs everywhere. Most of you have at least 3 or 4 JavaScript engines or interpreters just in your pockets or in your hands just right now. And the quantity of devices is really big, I would say. Once again, JavaScript should be very easy. You just type something and it works. But then, as I said, there was too much of it, and now we receive this beautiful picture of a lot of frameworks doing something for us, helping us, doing something, the world a better place, you know. This thing helps the world to become a better place. Well, they claim it like this. And the life of an application changed significantly. So if previously it was a web page, you load it or you render it in the server and you just deliver it to the client. Now, most of the time, we are using so-called SPA single-page applications. So you render the initial HTML, and then all the interaction comes with the JavaScript and the JSON going back and forth with asynchronous report and so on and so on. And to make this thing work, we are all, most of us, I'm not sure if all of us, but most of us are bound to this picture. We all use NPM. So, how many of you actually have not used NPM for application? Well, for example, the last year. No hand at all. Everybody uses NPM. And you see, every time you have a very, very small application, you still use NPM. And you say, oh my God, my application is only 3 lines, and it, you know, delivers the world's best experience so far and so on. And if you see that your application is really 2 lines, but then you have about several megabytes of dependencies which are loaded and help you do it under the curtains. Now I have the following question. Do you know what is this? You see, this is very fancy, and there are a lot of actually, well, it's written what it does. You will be surprised, but this is only this function in JavaScript. JavaScript should be so much versatile, so much, you know, easy, then the plus operator actually loads to this very fancy construction. So every time you do a plus operator, you think, oh my God, I'm just, you know, summing 1 plus 2. But then the JavaScript engine checks if 1 is integer, or if it's float, or it's string, or it's whatever. Then he checks if the second operator is also string, you know, or integer, or whatever. So every time you do this, just to produce this small portion of code, you have to do all these fancy checks. And every time you load something in a page, the JavaScript engine, which runs underneath, will have to parse this thing, perform, well, create an abstract syntax tree, and perform all of these checks that you have seen on this fancy picture. Now imagine how many carbon dioxide you produce every time you try to parse all of it, create an abstract syntax tree, optimize. Well, you do this on every device. It's so much versatile. You always lose a lot of cycles just to, you know, to initialize the application and see what it actually can do. So there were a lot of attempts to optimize this, and one of them is SMJS. So people say, okay, we have a problem, like, you know, Houston, we have a problem. Our interpreters are too slow, and the demands from the industry are so that we want to run almost on native speed on every device. So they have created SMJS, so the guys from Mozilla, they make it really cool, but it's actually a half measure, it's not a full measure. We still get a lot of performance. How many of you have seen this Unreal Engine in the browser? You play Unreal in the browser. Okay, your laptop totally melts down, but it still somehow gets you 30 frames, which is, whoa, like amazing. But SMJS does not do too much. It actually generates the same JavaScript code, but which is then annotated the way that the interpreter or the engine, JavaScript engine, understands it and does not do all of the fancy checks you've seen. He sees, okay, if it's like 0, like, you know, the first line x is x dash 0, that means that it can be only integer. It cannot be string. That's why I won't do all of the optimizations, all of the checks I need. And that's why we are just not checking them. This is actually the acceleration. And that's why we are able to perform all of these things. Now you see, Chrome browser, for example, is like an example. He sees that there is some code which we need for performance. Yes, he tries to optimize this code as he actually performs all this SMJS transformation for you, as he sees hot places. Hot places is the code that we call many times. And there is a thing called turbofont. This is just an example, so the Mozilla does it differently a little bit. But most of the time you still have to perform parsing, building a abstract syntax tree. Sorry about that. Then you can see the hot places, and then you try to optimize them. If it works, you try to de-optimize them, and so on and so on. So you're losing a lot of cycles for that, but you still need performance. You really need this performance. It's the demand of the market. And you need this performance not only in big machines like you have it, you need it on every small device. Like, you know, the mobile phones have to do almost the same. So people sit and thought, okay, we need something which should be mostly native, but not so much native, and it should not be Java Applet. So they had a committee. They made a committee, mostly of guys from Mozilla, Chrome, Safari, and even Microsoft guys. Sorry about that. And in 2015, they have created something which is called Webassembly. So Webassembly had to become a true savior of the world. Yes, it was claimed like the savior of the world. Why? Because there should be no more JavaScript. Yes, people say that was the same reaction from my side. My God, I won't need to write JavaScript anymore. I thought for myself that I will write a program like a programmer, then compile it, and send it to the browser, and it will work. So, what is actually WebAssembly? Wikipedia says it's a binary instruction format for a stack-based virtual machine, designed to be extremely portable, and be able to be compiled from many languages, like, you know, C++ to JavaScript, Python, and so on and so on. And the main idea is that this code should run on the client side, not on the server side, but on the client side, and it should run on every device, every browser, in every machine. And you know, actually they have succeeded. The first versions of WebAssembly, well, they were extremely fast. Up to, well, 20 times faster. Why? Just because we're not doing every time this compilation stuff, abstract syntax tree parsing, and so on and so on. And we are always smaller over the wire, so we don't send text, we send binary transmissions, let us say. So we send in binary format. So what they claim it to be, it should be, well, stack machine. Stack machine, that means that, there are register machines, register-based machines, like, the real processor register-based machines. There are stack-based machines, like, Java JVM is the stack-based machine. So WebAssembly should also be a stack-based machine. It should be extremely efficient. There was another demand, which is, very required right now. It should be sandboxed and should be implemented inside the virtual JavaScript machines that we have right now. So if we execute something, we should know where and how should we execute this thing. And this means that we should be able to provide full control and full security, the same as we provide in JavaScript right now, in JavaScript environment. Moreover, as you see, JavaScript guys, as they say, well, that was the only programming on client side, so it should be very easy. And they said, okay, it should be also very easy to be read and debugged, and seen and read, and you should be able to write it very easy. Moreover, it should follow the idea that there should be no compatibility issues at all. So there are so much devices that it should follow the model of versionless evaluation, let us say. Like actually mostly I would say the Java does. Everything which was running on previous versions of Java should run on the next JVMs and so on and so on. You will be surprised, but after 2015, we're 2019 already, by the way, it's already shipped within all of these browsers. You'll be surprised even in this browser it's shipped. That was kind of fancy for me. And the idea, once again, the main message that they sent, you will not be forced to program on JavaScript anymore. And well, it's not exactly what what we say. It's not exactly what we expected. So you should be surprised, but WebAssembly is not a full replacement of JavaScript. It's actually a good addendum, a very good part of the architecture that we have right now. So if we take a bigger picture, you remember this logo of WebAssembly. Actually, it fills the gap in the productive stuff of the client-side running code. So unlike doing all this preparations, parsings, and so on, you just get them off and you just get a WebAssembly binary and use it. This is the idea. So WebAssembly, the main idea of it was kind of a new capability for web. It should be not a replacement, it should be a new capability. It should still be interfaced from JavaScript, it should integrate with web APIs that we have right now, because there are lots of web APIs, like APIs for cameras, for tracking devices, for everything you have in your browser. You usually please turn off, please turn off, please turn off, don't track me. You don't want to know my location, and so on, so on. And it should be utilizing the most new technology that we have right now. So for example, we know that processors are multi-core right now, and so we can use threads, we should use threads. Or that the processors themselves are optimized for single instruction, multiple data. We have special instructions, so SIMD instructions should be also available. Once again, they should be very, very compact. Well, the WebAssemblies that we built, they were significantly smaller than ISM.js. That should be really easy to verify. What does it mean, easy to verify? That means if you load the JavaScript code, you still have to parse all of its parts to create this tree, abstract syntax tree, to see if it works, to see where are the problems, and so on and so on. And in WebAssembly, you just parse the assembly itself, one linear pass, and so on and so on. So the language itself, as they eventually came up, so this is the WebAssembly language. You only have 4 types for now, like integers and floats. You have all the standard operations. You can work with arrays, and you have structure control, so it's very easy. We will see it in real examples, I would say, just a few minutes. So the idea is that at current state of WebAssembly, we are able to run almost native speed, 1.2 the speed of a native speed. This is a kind of achievement, I would say, on almost every device. You go almost native. Of course, we want to use it. But to get this, we really need to get low, unfortunately, for now. We are programmers. We're not scared of running low code, low-level code. So once again, we integrate with JavaScript. We have to use the same security policies like it in JavaScript. Once again, we have to integrate to the same tooling that we have in JavaScript. Like, you know, if you want the debugger view or the developer instruments view, we'll still have to be able to do this. This is the founding principles of WebAssembly. So it can be WebAssembly, the resulting WebAssembly can be both binary and text format. So here you can see a small example of a real working WebAssembly program. It's really like, you know, exactly assembly, so it comes from the name. It's like, you know, taking a function and doing something with it. And this is also a good example of how we can transform every C++ programmer to a WebAssembly. This means that we are most of the time would be able to run a C program, which we used to run all the time. How many of you actually coded C in production? Oh, good. Okay, how many of you coded C in university? Okay, so we are back to university times. And we take a C program and we compile it to a program in WebAssembly, which is very close to, as understanding, as an LLVM. So C, just because the C is the father of everything, I'll call it like this. And WebAssembly is so young, it's definitely very, very young. So to understand it, we still have to think a little bit in C. So once again, the main objective of the initial release is called the MVP, so it's not the most valuable project, valuable professionals like, you know, in Microsoft. It's the most viable product. It's really the minimal configuration of the language itself that we can use in production. Still no garbage collection, and we heavily rely on LLVM for the compiler tools. So what does it mean, MVP? That means that the specification of WebAssembly is still in progress. I mean, not everything is available right now. We still can use very, very basic things, but as you probably see, not everything is implemented. What's wrong? Sorry about that. Good. Yep. Just a second. But that was just a theory. I want to make something working when I had 30. So for this, we will use some infrastructure. So if you want to play with WebAssembly, most of the time you will play with mscripten, or binarian, but mscripten is the best choice for now, I guess. So imagine, this will be the pure hello world. This is, as you see, a C code, just because of the hash include, stdoh. As a result, We only need to take this file and give it to mscript in CC, and let us see what will happen. Just give me a second. I have prepared it. Can you see it from here? Good. Just give me a second, yes. Good. Wow. What was the way to make it bigger? Like this. Yep. I think. Colleagues, we have technical issue. It's not working anymore. I'm sorry for that. But as you probably see, it's not showing anything anymore. Well, this is the first run of the code. That's why I'm so much nervous, and that's why the demo codes are always, making something to us. You could put everything out, I guess. And then put it inside. Well, I don't see any image at all. Okay. Well, it looks better, I guess. No. Okay, you can see it. Okay, it works, so thank you. Okay, so you have an infrastructure. We make an MCC comment, say the main part here is the WASM equals 1. And hello HTML. We'll also add an AM run, but this is just an option. Okay, something's happening. He compiles the C, he runs a Clang compiler, transforms it to LLVM, and then takes the LLVM and produces what we say, you see, a WASM. So we have produced from C code and page hello HTML, some JavaScript, which is a little bit unexpected, but still we have produced it, and then the WASM file. So mscripten has a very good infrastructure, once again I said. And then we have a built-in server to see if it runs correctly. Good. Now we will have to open the browser. Localhost. Okay, I'll make it a little bit bigger. And good, what we see? We see an mscripted console which runs the hello world for us. So for me as a programmer, this is enough. I mean, for me, it's okay to run everything in console mode. But we are not console people. So that's why WebAssembly, if you run it, we run it through so-called infrastructure. So we have JavaScript infrastructure. There's a special JavaScript file here, which actually combines what we have. Well, it generates a lot of code as well. But here this is the binding code between JavaScript and the WebAssembly file. So we passed it to browser, and then it creates everything for us. But we don't want, this is just to print the console actually. But in real world, we'll make a different example. So we can even call a function from outside. I'm sorry. Yes. So I've already compiled it, and I've even made a make file, so back to the C ages. So if we run this thing, open dots, we will see that we have an HTML page, and I have created, so this is actually the code. It's very C-ish code. This is the purpose of life, of course. Yep. it should be a very long computation, but I just say the purpose of life is this. Then we have created some JavaScript. This is actually the binding part. This means that, oh, once again, something's wrong. Something's wrong. Yeah. We definitely have problems with converters here. Maybe you should try something else. Maybe have another converter. Although this is the original one. Oh, this is the same. No. No. This is not gonna work. Yeah. This is not gonna work. This is USB-C actually. Okay, he also has one. Oh. Okay, let us try it. Maybe it should work better. Okay, once again, technical issues. You can put it wherever you want. I have 4 USB-Cs. It's a MacBook Pro, the most expensive one. I think that the problem is not on my side, or even not the converter side. Maybe somewhere from here. I'll try it again. It runs on battery. No, I don't think so. No, just give me a second. Now it's like video. So there's monitors. Okay, it's V1. Maybe I should put a 18p. I, okay. Well, it's I. It's P. This is Flash technology right now. Well, if you give yours, maybe it will work. Just put it in every USB you want. The funny thing that it was working. Oh, good. Thank you, Emily. You're the savers. Yeah, good. Okay, and it's working in 1080p, which is good. Okay, so here we create some binding from our code, which is which is JavaScript. We call the WebAssembly. So that means there are special instructions, and there's a special library for WebAssemblies, like instantiate. We take the WASM file, which is the compiled file. We take the results. It's nice, done, beautifully asynchronous, and then we just print elements. Like we take the result from WebAssembly, and it works. So if we, not to lose time, so every time we do this, this means that we do not cancel HTML at all. So we built like inside, WASM file itself lives inside the JavaScript engine. So most of the time they talk to each other absolutely natively. That means that we can call external functions as well. So this is a C code. There is an extern keyword here that is say, okay, print value is something that will come to us. And then we say, this is already the client-side code. Everything actually is the client-side code. We say, okay, so if we have this, we have a function that prints something, and we just call it. So we pass it to WebAssembly, and it works. In our case, we just say, okay, this label should be printed the value. Okay, once again, not to lose time, we can move data back and forth. This is the tricky part actually. So as the data may be only in binary format, it cannot be like, you know, this JSONs we use, and it should be moved in chunks like called pages, and each page is about 64K. So and the memory model is very low level, I would say. So the page access, the memory access is done via offsets. So if we imagine there is an algorithm like, you know, scalar add, so we just add value from an input array. This will be the program that actually sets everything for building from inside JavaScript to WebAssembly. So we first allocate the memory. Then we said, okay, this is our WebAssembly that we're going to use, scalar add. We have infrastructure to see where actually this memory is allocated via a function of offset, because now we are working in this pointers that but when Kat was talking later, we're back to the ages of structural programming now. Then we say, okay, we want it to be integer, and then we'll just call it. And not to lose time, this will definitely work. So about working on our machine, it does work. But what about debugging? So as you probably saw, we were running code like this. If we add just the parameter g, it will pretty print our program. But we don't need any pretty print, so we want to go and use it in browser. So there's a bigger command that's we're going to use it right now, and this will help us to debug directly in our browser. So let me demonstrate this for you. We will go to the 6, I guess, was debug. I've already prepared, there is an add command, so it's just make add operation. It's very easy. Open dot. Good. So it's a very easy program. It's just returning a plus b, and we want to debug it. So we have this infrastructure, so we built, like we export everything. Wait a minute, yes. Okay, MCC. Okay, demagogues as always, but nonetheless, we already have it compiled already. So if we run it, run in the browser, and we'll listen to the command. They should be, well, as we say, debugging tool. We will go, so we have the connecting code. Okay, great. If we take a look at the code, there is a sources. Okay, it's not linked right now. The demagogues are always like this. Sincerely hope it will work right now. AMCC 0C. Just give me another trial, please. So I generated the map command. Modal add 04. Okay, that's low level. I wrote no such file or direct directory. This is strange. Okay, I'll make it a little bit different. I should probably have it in my, yep. It did compile it to us. Yes, now we have to just mrun it. Let us see what we have loaded. Yes, as you probably see, directly in the debugger, we now have this add C file. This means that we can debug it directly with the tools inside the browser. So it's all browser based. And okay, this is low level, I know. Most of you are Java developers here, and it's boring. So we want Java. And for that, we have several projects. Well, the first one is Webassembly, which is a kind of an unofficial way to do this. And the second unofficial way to do this is the TVM. So if we take a look at the WebAssembly, we start coding in Java like in a usual way. And most of the time, you just have to add annotation to some code, and then out of that class, it will produce you the WebAssembly. So, and you will be able just directly use it in the code. Let us have a look. And so we are now closer to real world. JWebAssembly. So, like for example, I have an add operation. I just say, okay, I want to export this operation and say this will go to WebAssembly. And there's a special runner I wrote for it. So it's not the best way to represent, but you don't have much to look in the code. But it's just, you know, using the WebAssembly file, add a file, and compile to text. So if we run it, we will see that it will compile us an string as expression, like string expression annotation of our program. So this right here is a WebAssembly program that we will able to use. You see, in our ideas, we can use many other algorithms directly, like quicksort. This is just a usual quicksort. I don't have 5 minutes, or I have technical problems, plus 10 minutes. Yes. We're able to run it, and this is a usual quicksort. So if we run it, it will generate us the quicksort. I guess this is, yep, quicksort, which is kind of cool. This is the quicksort program in WebAssembly. You see, it's directly out of the Java. I'll just show it to you as, well, it's working. You see, like a stack-based machine. And we're generating it directly out of the Java. So unfortunately, it's not almost everything supported. So if we go to matrix multiplications, which uses, for example, two-dimensional arrays, our example will not work. So Java is still making the first steps in converting the WebAssembly as it is. Like for example, if we add another dimension to data structure, which is not something strange, it's just, you know, double two-dimensional array, it will not work. So there's still a lot of things to be done. But in our case, there is another option. You see, we can do this. There is a library for this. It generates this. Another thing is a very cool Russian machine called TVM. It actually started from the idea that we should take a Java and convert it and transpile it to JavaScript. But then they say, okay, first of all, it can be Java, or it can be Scala, or it can be Kotlin, any JVL images. And then we say, why should it only be JavaScript? And we can transpile it directly to WebAssembly. And this is the most civilized way right now to produce, to use Java in real-world production as a part of our process. So let us see some example. I'll show it. So we have a very basic algorithm, which is, of course, the purpose of life. Imagine there is a very strong computation here, like, you know, something very heavy. As you say, we just export it. This means that this function will be exported to the outer world and be accessible as a model in WebAssembly. Then we go to the Maven page and say, okay, we need the TVM, And there is just one small plugin here, like here. And we say, okay guys, please take this class and make it WebAssembly. And probably that's it. It will generate everything as we want. Well, I'm not sure if it's a good idea to compile it right now, but I will do my best. So if we just go and make an install, it will perform full cycle of development. I mean, so we will take a usual application, we will just take some of the classes and make them WebAssembly and put it in the web folder. Actually, this will go to the client and be working on the client. So I guess, oh, there's a server. It is set up. I sincerely believe it will work. It just takes the WAR file that we have. Oh, okay, something is already in use. We have to stop the MCC, run it once again. This will mean that we have performed everything as a cycle. We can code directly Java, only in Java. We only add some annotations and say that we need to add some classes and make it on the client side. So it will compile the WebAssembly for us. It will compile all the binding JSF. And you see from here that this is calculated on the client side. This means that we run a usual Java, we use it in a usual Java cycle, let us say, and it just goes directly to the client as a WebAssembly connected to with the JavaScript, as he says, as I was mentioning before, and this is it. This is already Java. Okay, so as you probably saw, the idea is just add some TVM APIs, annotate your function, say that this class should be compiled to WebAssembly, made a plugin to TVM, and it's it. That's it. So we have shown you the demo already. So how many of you recognize this picture? So it's just an island, yes? Maybe you should better recognize it like this. What about the Kotlin? So you know Kotlin is an island near St. Petersburg where the Kotlin language is created. So I can see it from my windows when I'm at home in St. Petersburg. So the Kotlin island. So how did Kotlin do this? Of course, they did it their own way. There is a big project called Kotlin Native. Well, Kotlin started as a JVM language, you know, so it was an alternative to Java. But then they tried and make some experiments and make this Kotlin Native. By the way, tomorrow is going to be a talk about Kotlin Native by a guy also called Dmitry that will be coding in Kotlin but produce native code. But Kotlin itself, as it runs, it produces LLVM. And since we have LLVM, you have heard of LLVM, I guess. Some of you? Well, okay. It's a low-level virtual machine, so-called. It produces LLVM code, and since we have LLVM, we can produce out of it WebAssembly. And we'll see how it goes in Kotlin. We'll run a function, which is just the usual function. Then we have a build script, and the only thing we actually change is the target. So we only say, okay, this class should be compiled as a WebAssembly. And we will see how it goes. So once again, I have prepared a small demo in Kotlin. It's once again the purpose of life. So Kotlin native. There is a function, as always. Very, very long computation should be here. And we'll say it's not 42, it's 43, because we can afford it. There is a view function which is specific to Kotlin. I mean, so we render the results like this, and we just call it. So we call fill the purpose of life, and that's it. And after we compile it, builds. It sometimes may take some time, but the most of the idea is that it also generates us the output, the HTML itself, the components that we want, and also the binding JS. As you probably see, it generates us WASM file. So this is the WebAssembly file and a JS file, which actually regulates our yeah, it did good. It regulates our relationship in the browser, so it orchestrates. And now if we run this code, I guess, yes, that's the one. Okay, we have several minutes left. Now, wait a minute. Oh, we have to go to the web, sorry. The web folder. Ah, yes, we are inside actually web. Okay, so it's 5,000, I guess. Wait a minute. Let us refresh it. Synchronize. Oh yes, we have to, it's not the index, we should use the output page. Okay, the output HTML, and ta-dam, the purpose of life is 43. This interesting thing, if we go to code of the page and see the console itself, we see this like print lines inside. This means that Kotlin has a colon compile. If we just print line the function inside the Kotlin code, it will automatically bind our JavaScript output to the Kotlin language classes, let us say output. So we can just print line and it will just go to the console. So this is all browser. It all runs in browser in WebAssembly. So the main question is, why should we do this? Yes? Why all this exercise? So of course, we can mine bitcoins on clients' machines. Nobody will understand that it's so tiny WebAssembly. But I come from Deutsche Telekom, and this is a bloody enterprise. And you know that every program in bloody enterprise sooner or later becomes an Excel sheet. No matter what you do, it all ends up in being an interface close to an Excel sheet. And many of the processes there in Deutsche Telekom are just, okay, take this Excel file, find a column, put something inside, and send it to somebody else. Like in our situation, we had some 4.5-year Excel file, which is 200 megabytes big, and we send it as in emails, and different people in the process just, fill in some columns and so on and so on. And they have to do sorting. They say, okay, we have to do it the modern way. We have to do it in browser. And that's why we did something like, a table, a component. It's like a Google spreadsheet. It all runs inside the browser. And it works. So it worked. But it worked in our environment when we have only 2 lines of code or 3 columns used. The real world sheets are, we have a new record. We have no columns left in our sheet. That means that all 65,000 or something like this rows were in use. So you can imagine how many information we have to process there. I don't know why they do it. But in a certain moment we have created this, they have filled it with data, they open in their iPad, and they click only one function, which is sort. And it takes them several minutes just all these entries to be sorted, just because it's done in JavaScript. So that's why the usual thing like quicksort, we have rewritten it in WebAssembly, and we have received really good results. Even in the bloody enterprise, we still have place something to be accelerated. And that's why I'm actually doing this talk, because we have implemented WebAssemblies on client side. We can do the usual sorting. And it's a very simple function, and it still works. So you may say, we've seen it all before, like, Java or Flash. Many things like this were done. That was even not even born, I would say, like, this Google stuff native CL environment. They have one problem. They are all private. That means that they are developed by one company, and they are all managed and ruled only by this company. On the other side, WebAssembly is a standard. That means it runs on every browser the same way, no matter actually which browser it is and how this WebAssembly is produced. So it runs as a standard. And it's a very interesting thing that it's already integrated. So it's already there. And as a idea that I want to say in this talk, so most of the time you may not use WebAssembly, but it's good you to use it just because you have to remember this picture. This is something I have printed on my wall and put it, and see, every time I do JavaScript code, I watch this picture. So now imagine how many cycles are burned out. So save the planet. Don't burn additional cycles. And are we back to the applets? I sincerely say no, we are not back to the applets. Yes. And probably that was something I wanted to share with you. So thank you very much. Thank you.